quick review of evaluating logarithms without the aid of a calculator, meaning that we're going to learn some methods to help us handle questions that aren't as easy as answering this one. So if I ask for the answer of the log of 36 to the base 6, Rebecca, you would say the answer is 2. Now, why is the answer 2, Rebecca? Exactly. Okay? So 2 is the exponent that you would put on this base 6 in order to get 36 as an answer. Say you didn't know that. Say it wasn't as obvious and you wanted a way to solve it. Then if you don't know the answer, and again, you wouldn't have to do that in this case, but I just want to give you a way to solve it so that you can do the harder ones. Say you didn't know the answer. Say, okay, I don't know what the answer is, but I'm going to call it x. But once I write it now in log form, I can write it in exponential form. So the 36 stays, the 6 comes over, becomes the base, and the x becomes an exponent. And then really you're just reaching back to grade 11 and solving exponential equations where the base can be made the same. Once the bases are made the same, you equate the exponents. So if you get a question like this on a test, and you will, and it's the answer is obvious, you can just write down 2. It's going to be worth 1 mark. Okay. A more complex one, I'm going to be looking for some of the process to get your answer. So if I ask what the log of 1/4 to the base 8 is, maybe that's not as obvious as an answer. By the end of the course, we're going to be able to figure how to do this on a calculator, because on a calculator we only have 2 log buttons, the log base 10 and the log base e. So in order for me to combat that you just didn't use your calculator, I'm going to want to see work for the harder ones. So you're going to say, you know what, I don't know what the answer is. The answer is x. But once I write it in log form, then I can write it in exponential form. To write this in exponential form, I get 1/4 is equal to 8 to the exponent x. Now you're solving an exponential equation where the bases can be made the same. So 2 can be used as a common base because 2 to the power 2 is 4. And 2 to the power 3 is equal to 8. Okay, so I don't quite have the bases the same because I have this base in the denominator. I want to move it to the numerator. How do I do that? Okay. Make the exponent negative. Excellent. And on this side, I have 2 to the power 3 raised to the power x. So I raise a power to an exponent. I multiply them. And once the bases are made the same, then I can equate the exponents. Divide both sides by 3. And the answer to my question is -2. So you get a question like this on a test. You're going to want to see work. It's going to be worth 2 marks, 1 for the answer and 1 for the process. Any questions on that? Okay. Now I'm just going to use some evaluating skills that we learned in order to generalize some rules for solving logarithmic expressions. If I ask what the answer to this question is, everyone want to take a stab at what that answer to that question is? Lucas? So remember what Dean?
It's 4.
4. Why is it 4?
Because log of the 8 is, or the log is to the base 8.
Yep.
So whatever it must be equal to has to be equal to the power of 4. So you want to okay.
Yeah, exactly. Okay, so just let me kind of reiterate what you said. So remember that a log says what exponent do I have to put on this base to get this answer? Exact same question. What exponent do I have to put on 8 in order to get 8 to the power 4? That's obviously 4. Right? That's what Dean was saying. Does that make sense? So we're going to make a generalization that if I have the log of a to any exponent to the base a, then the answer to that is going to be what? X. The next one is a little bit harder to see, but I'm going to write down a logarithmic expression. So I want to solve this, okay? So in order to solve this, again, I don't know what the answer is, so I'm going to say let the answer be y in this case, because there's already an x there, so I can't use x again. So now I've changed this exponential expression into an exponential equation by writing them equal, and if I have it in exponential form, I can write it in log form. So to write this in log form, this is the base in the exponential, so the 2 becomes the base in the log, so the exponent moves down. The 2 becomes the base on the log. And when you have the log of x to the base 2 is equal to the log of y to the base 2, when you have logs where the bases are the same, then you can say that x must be equal to y. Okay, just like back here when we were solving, we had the same bases, we equated the exponents. When you have the same logs, you can equate the intervals. Okay? So that leads to this law that if you have a to the exponent, the log of x to the base a, and again, the bases have to match. If that matches, then the answer is x. So that'll help you in solving some logarithmic expressions in your homework. Question E. So the log of -9 to the base 3. So what exponent do I have to put on 3 in order to get -9 as an answer? Anybody take a stab at that one? Tiger? Negative. What? Hold on, like. So you say, hold on. -1 to the power 2, that? But remember, the base has to be 3, right? So say, what exponent do I have to put on 3 to get -9 as an answer? Again, if you're not sure, say, you know what, I don't know what it is. So I'm going to call it x. Write it in exponential form. So what exponent, the exact same thing, what exponent do I put on 3 in order to get -9? David? -2. So if I put, just as an aside here, so Dave say -2. 3 to the -2 becomes 1 over that, which is 1 over 9. Is that -9? Nope, so that doesn't work. Keeping in mind in mathematics is not always an answer, right? So, do you think I can do this? No, you can't. It's not possible. So it's not possible in order to take the log of a negative number. There's no way of putting an exponent on a base and making it negative. That's impossible. Okay? In much the same fashion, there's no way of taking any base, putting an exponent on it, and making the answer 0. Okay, so this is impossible either. So you can never take the log of a negative number, and you can never take the log of 0. Is this possible? Lucas, what's that is? Sure. Because this is saying, what exponent do I have to put on 8 to get 1 as an answer? And anything to the power 0 is 1. To answer that question. Okay, we good on some evaluating this stuff? Keeping in mind, right, what log functions mean. It's just saying when you see the log of something to the base, it means what exponent you have to put on that base to get that answer. That's all a log means. So let's graph one so we can look at the graph and discuss the graph like we did the exponential graphs. So graph the function y is equal to the log of x to the base 2. So we're going to graph that guy, and we're also going to graph its inverse. Okay. So we're going to graph the function y is equal to x to the base 2, and we're also going to graph the inverse of this function. Okay, so here is the one I want to graph. Also, I want to graph the inverse of that. What's the inverse of that function? Yeah. Exactly. Where did he get that from? Well, we learned in the very first day that logarithmic functions are the inverse of exponential functions. Okay? And if you're not sure which one it is, take your log function, write it in exponential form. So remember, this means the exact same thing as this, and if you want to find the inverse, just switch the x to the y, and that's how we got the inverse. We've already graphed this one, so it's fairly easy to graph it again. Just do your table of values. So graphing the inverse we've already done, so I'm just going to do that quickly. Okay, so that's the inverse. How do I graph the log function? Because it's the log of x to the base 2. There's no base 2 button on a calculator. Anybody tell me a quick way of graphing an inverse from its inverse? Yep. Yeah, exactly. We have the points now. Just switch the order. It becomes 1/8 and -3, 1/4 and -2, 1/2 and -1, 1 and 0, 2 and 1, 4 and 2, 8 and 3. I'll do this one in red. So the red one is the graph of y is equal to the log of x to the base 2. But we're going to use that to generalize all logarithmic functions in that form. Okay? So you'll see that the red graph never crosses over to the negative side, and that's why we can never take the log of a negative number, because it's never on the negative side. And the red graph gets closer and closer, but never ever touches the y-axis, so it never ever touches 0. So that's why we can't take the log of 0. Okay? So making some generalizations about the red graph. I'll do red. What's the domain of it? Look at. Awesome. So x is any single real number. So you can take the log of any positive real number and get the answer. Okay, that's what the domain means. The range, so your answers will range from what values can your answers be? Lucas again in the same category. This pause up here. Does it ever go down to the negatives? Right. Okay, because here it's heading down to negative infinity, so it's going to pass through all the negative numbers. Here it's heading up to positive infinity, a little bit slower than it's heading down to negative infinity, but it's heading up there eventually. Okay, so it's an element of all the real numbers. Just like the exponential has an asymptote, the logarithmics have asymptotes, except having a horizontal one, it has a vertical one. So it has a vertical asymptote at x equal to 0, or it's the y-axis. And just like all the exponential functions pass through the point 0 and 1, all the logarithmic functions are going to pass through the point 1 and 0. Okay? Okay, so now we have a general idea of what the logarithmic function looks like. And keeping in mind, it's just the inverse of the exponential function. Okay? So to the inverse, you switch the x and the y's, right? So the domain of the inverse happens to be the range of the exponential, and the range of the inverse happens to be the domain of the exponential. That's what happens when you switch the x and the y. Any questions on that? Okay. Now the most important thing that you're going to learn in this section to be successful, which is the laws of logarithms. Back in grade 9 or maybe grade 10, you learned the exponent laws, right? Multiplying powers of the same base, you add the exponents, dividing powers of the same base, you subtract, raising an exponent to an exponent, you multiply. Because logs are the inverse of exponentials, it only makes sense that there's laws for these guys. We can actually prove these laws, and it's done for you, I think, as a homework question, so I'll leave that for you to try. But if you have the log of something, which I'm going to call m, to a base, which I'm just going to call a, and you add it to the log of something else, which I'm going to call n, to the base a, that's the important thing. The bases have to be the same. Just like when using the exponent laws, the bases have to be the same. You can combine these two into a single logarithm by multiplying the m times the n. How is this useful? I'll just show you a very simple example of how this is useful. Evaluate without a calculator. The log of 2 added to the log of 3. So remember, the log of 2 is just a quicker way of writing down the log of 2 to the base 10. Remember, whenever there's a base there, it's understood to be a 10, not a 1. That's a common mistake people make all the time. Okay? So this is just a quicker way of writing it down because the base 10 scale is a very important scale. They use it for decibels, for pH scales, for Richter scale. Everything is at the base 10. That's why they use it a lot, so they want us to leave off the 10. So this is saying, what exponent do I have to put on 10 in order to get 2 as an answer? Well, that's some decimal, right? What exponent do I have to put on 10 to get 50 as an answer? That's another decimal. Okay? So I can't figure out the exact value without using the laws of logarithms. The laws of logarithms say that if I have the log of something to a base plus the log of something else with the same base, I can combine them into a single logarithm by multiplying the two parts. Now this becomes the log of 2 times 50, which is 100, to the base 10, and that answer is 2. Because what exponent you have to put on 10 in order to get 100? That would be 2. So that's where the laws of logarithms come in helpful for evaluating. Because they're so important, we're going to practice using the laws in the next couple of examples. Before we do that, let's learn the other two. The second one is when you have the log of something, base A, subtract. Knowing what you know about your exponent laws, what do you think this law is? Because when you divided powers of the same base, you did what to the exponents, Kyle? Yeah, exactly. Okay, that's exactly why. Because when you divide powers with the same base, you ended up subtracting the exponents. So when you combine a log that's subtracted, then it combines into the first thing divided by the second thing. Okay, in brackets is the log of that. And then the last one is when you have a number multiplied by a log, and you don't want that number in front of the log anymore, you can take it and write it as an exponent to the end. That's very important law, because to use law 1 or law 2, you'll notice that there's no numbers in front of the logs here. When I say there's no number, there's a number 1, but you can never have a number in front of these guys in order to use your logs. Okay, so that's how we're going to get rid of our numbers, by doing that. Okay, so we're going to use these 3 laws in order to expand and simplify logarithmic expressions. The first one we're going to do is simplify. So we're going to express as a single logarithm. First question, we're going to I want to take the expression, the log of x to the base 3 plus 3 times the log of y to the base 3 minus 4 times the log of z to the base 3, and write it as a single logarithm. So I want it just to have log and then the inner parts. Okay? So in order to do this, David, I have to use the laws of logarithm. Okay? There's only 3 of them. Okay? When you multiply, when you add, you multiply. When you subtract, you divide. And if you don't want a number in front of the logarithm, you have to move it up as an exponent. Okay? And you can't have any numbers in front of the logarithms to use the first 2 laws. So the first step I'm going to do is I'm going to take any number that's in front of my log and move them up as an exponent. The first guy doesn't have a number, so I'm going to leave it like that. This guy has a 3, so I take the 3, and I move it up as an exponent on the y. The next one has a 4 in front of it. I don't want that 4, so I move it up as an exponent on the z. So now I have it in a form in which I can use the first 2 laws. Okay, so I can use the addition law or the subtraction law. So to combine this into a single logarithm, the log of x to the base 3 plus the log of y to the exponent 3 to the base 3 can be combined into a single logarithm by multiplying it. Subtract the log of z. Now to combine this into a single logarithm, I'm going to use my second law, and I divide it. So I've taken an expression that was an expanded form, and I've written it as a single logarithm. Okay. Any questions? Okay, so let's try a harder one. Okay. So in order to use the laws of logarithms, the first 2, the addition and the subtraction, you can't have any coefficients other than 1 in front of your logs. The first thing you want to do is get rid of your numbers in front. So I have a minus 1/4. That minus 1/4 is going to come up and become an exponent on the a. I have to take the 1/4, that's a number. Also, I have to take the negative, because I can't have a negative, right? The laws are a positive log, subtract or add it to another one. Okay? So since there's 2 laws for adding and subtracting, when I take the next number, I can just take the 2/3 up there, because that doesn't matter if there's a negative now, after the first one. And then my last one, that makes sense. I just take all the numbers, move them in front. Okay. This guy didn't have to take a negative because it doesn't matter if there's a negative afterwards because that's when we lost. We good with that? Okay. So then how do I combine these two guys together? What do I do to them? Divide. So this one is going to be a little bit more effort than the last one because I can simplify what's inside of the bracket. Right? So I can simplify a to the negative 1/4 divided by a to the 2/3. Now I have to remember, going back to grade 9 or 10 when we first learned our exponent laws, is when I divide powers of the same base, I keep the base, and I subtract the exponents. Okay? So if I was doing this, which I actually am, I would use my calculator. I would go 1/4 negative, subtract 2/3, and my calculator would give me the answer of negative 11/12. If you don't know how to use your fraction button on your calculator, it's very useful, and I can show you how to do it. Okay. Plus combine these into a single logarithm. To combine them into a single logarithm, since I'm adding, I now multiply the inner parts. And again, because the bases are the same, I can simplify. When multiplying powers of the same base, I keep the base and I add the exponents. And again, you can do that right on your calculator. Add that one, make sure we did it correctly, and negative 5/12. Any questions? Okay. Then we want to be able to do the reverse. Okay? So the reverse is taking something that is in a single log and writing it back into expanded form. Example, express in expanded form. The log of the square root of b to the power 3 divided by the 4th root of c to the base 7. Okay, so the first thing that we did when we expanded was get rid of all the exponents. Right, move them up. Here, the first thing I'm going to do is get some exponents by changing all my radicals into the exponent form. So remember that the square root of a in exponential form means a to the 1/2 multiplied by b to the 1/3 over the 4th root of c is c to the 1/4. And all of that is to the base 7. So now I want to start to split this up using my laws. Which law can I use first? Right, the second one. The second one says if I have the log of something divided by something, going back over here, so the log of something divided by something, I split it up into the log of the first guy, subtract the log of the second guy. So that's what I'm going to do here. It becomes the log first part, subtract the log of the second. Okay, so now I can still split up this a and the b. Which law am I going to use to split those guys up? Okay, first one. So it becomes the log of a to the 1/2 to the base 7 plus the log of b to the 3 to the base 7 subtract. Okay, I don't have it in expanded form yet. This is one of the most common mistakes people make, is they leave it like this. To have it in fully expanded form, I have to take my exponents and move them down in front. So that's your very last step. Take the 1/2. The 3 and the 1/4 and move them down as coefficients in front of the log. to the base 7, I forgot here and here. And now you've written in fully expanded. Okay, some common errors I want to talk about that I guarantee somebody's going to make. If I ask you to combine this into a single logarithm, I'm going to write down what most people write down. And then somebody's going to tell me, hopefully, why that's wrong. Exactly. That negative screws everything up. Okay? So this isn't equal to that. So in order to use your second law of logarithms, you have to get rid of this negative. So what do I do with it? Factor it out. That's one option. So I could factor out the negative. If I factor out the negative, I get that. Then I can use my first law of logarithms inside. And I get that. Then I can, it's an equal sign. Then I could take that negative and move it up as an exponent. And then if I wanted to even make it look prettier, a to the negative 1 is 1 over a, b to the negative 1 is 1 over b. So that would be the answer. Okay. Say I didn't want to factor it out. What were you going to have?
I would say counting as negative 1 and put
Awesome. So if you do that, then you're using the second law of logarithms, which is that. And then a to the negative 1 brings it down, and you end up with the same answer. Okay? But either way, it doesn't matter which one you do it, it's definitely not equal to this. And I guarantee somebody's going to do that with that. Also, a log is a function. Okay? So this doesn't make any sense. If I ask you the log of a plus b plus the log of a, I get people saying, okay, the log of a plus b must be equal to the log of a plus the log of b plus the log of a. What are they doing? Okay. Right, they're expanding. They're thinking, oh, this is something I can multiply into this bracket. That makes absolutely no sense. Okay? This is a function. There's nothing you can do with it. That doesn't make any sense. The only thing you can do with it would be to use the first law of logarithms and write it as a plus b times a. That's the only thing you can do with it. Okay? So remember, the log is a function. Okay? It's not a coefficient. You can't multiply it in. Right? So if I ask a question like to simplify that, there's nothing you can do with it. Okay. Yeah, you should. I just stopped doing it. Yeah, sorry. So that it would be a squared plus 3. Okay. So if you understood today's lesson, you've gone a long way to be successful in this guide, because really the the laws of logarithms are really the most important thing.